let me start. All right, everyone. Welcome to the VAMO seminar today. It is my great pleasure to introduce my good friend Hannes Pichler. Hannes did his PhD in the group of Peter Zoller in Innsbruck. Already during his PhD, Hannes had a history of getting me into trouble whenever we hung out. In addition to that, he also did some work on a number of quite impactful ideas already during his PhD, including, for example, how to leverage photonic circuits with time delays and feedback. After his PhD, Hannes spent time as an ITAM postdoctoral fellow at Harvard, as well as a Moore postdoctoral fellow at Caltech. In a true return to his roots, since last year, Hannes has established his own group as a professor at the University of Innsbruck and as a junior group leader at the Institute for Quantum Optics and Quantum Information within the Austrian Academy of Sciences. Broadly speaking, his group is interested in theoretical quantum optics, especially in the context of quantum many-body physics and quantum information. And as we'll hear about today, most recently, his research has focused on quantum technologies with individually trapped neutral Rydberg atoms. Take it away, Hannes.
Thanks, Norm, for this kind introduction, and thanks to the panel for organizing this amazing seminar series and for giving me the opportunity to present here some of the work that I've been doing over the last couple of years on Rydberg atom arrays. Sort of most of the work that I'm going to present today will be I've done as part of a collaboration with an experimental effort at Harvard and MIT led by Misha Lukin, Markus Greiner, and Vladan Vuletic. And so, as I said, this talk will be about the physics of Rydberg atom arrays. And as many of you know, Rydberg atom arrays, or atom arrays in general, have emerged over the last couple of years as a novel platform to study many-body physics. Neutral atoms, individually trapped neutral atoms in optical tweezers, have a couple of very interesting properties that make them especially suitable for studying many-body physics. In particular, one can use these optical tweezers to trap individual atoms and control their position, atom by atom, in various geometries. This goes from one-dimensional to two-dimensional and even three-dimensional arrays, where people in various groups around the world have now developed the capabilities to deterministically arrange atoms and positions as they want. It's a very scalable approach. People nowadays routinely assemble several hundred of these atoms in essentially defect-free arrays. One can then make use of the internal degrees of freedom of these atoms to realize spin models that have a high degree of coherence. They are essentially to a high degree shielded from the environment, and one can really study almost unitary many-body dynamics with a large number of individual particles. And they have strong interactions that come from the fact that one excites them to Rydberg states. And in addition, one has a large degree of dynamic control over many of the parameters that enter these Hamiltonians that describe these Rydberg atom arrays. And in the end, one can even do sort of in situ measurements and read out individual states of each of these atoms to gain information about the quantum many-body state here. And what I would like to do today in this talk is to tell you how one can sort of combine this system, these features, and study really many-body physics in various regimes, and then not also study many-body physics, but essentially also apply these tools to implement quantum information processing algorithms, and bring this platform towards really quantum computing, realizing quantum computing tasks. Okay, so in this sense, I will structure my talk in two parts. In the first part, I will talk about quantum many-body physics and Rydberg atom arrays in the context of quantum simulation. And then the second part will be about quantum optimization and quantum algorithms. Okay, with this, let me just start right away and give you sort of a theorists, crash course on Rydberg atom array physics. So as I said, what these experiments do essentially is they use optical tweezers to trap individual atoms, and one can really load a single tweezer with a single atom. And to study now many-body physics, what one does is one makes use of the internal structure of each of these atoms. At Harvard, for example, they use rubidium atoms, where you have an internal ground state, which is a 5s1 half state, and you can excite this ground state to a highly excited Rydberg state with a very large principal quantum number, typically something between 50 and 80. And you can, couple these two states with an external laser field. Depending on, which Rydberg state you go, you can go with a single photon to a p state, or what they do at Harvard, typically with a 2-photon transition via an intermediate short-lived p state to an s state in the Rydberg manifold. And essentially, this realizes then a 2-level system. Both of these states are fairly long-lived. I mean, this is a ground state. This Rydberg state has a lifetime of a few hundred microseconds. So it's, to a good approximation, we can just think about this as a qubit, which now has a Rabi frequency in the detuning, and so there's a single particle term in the Hamiltonian that describes sort of the single particle physics, which is the one we all know. But of course, the interesting physics comes about when you now consider many of these atoms and the way they interact. And these atoms interact in a very specific way. In particular, they interact only if you have two atoms and both of them are excited to the Rydberg state. So that means that if you have two atoms here and one of the atoms is in the ground state, the second atom doesn't really know about the presence of the first atom on these distances that are relevant for these tweezer arrays, which are sort of micrometer distances. So, but on the other hand, if this first atom is excited to the Rydberg state, what happens is that the transition frequency of the second atom now starts to depend on the distance between these atoms. And the reason is these two, if two atoms are in the Rydberg state, they are strong induced dipole-dipole interactions that have this particular 1 over distance to the 6th power dependence. So if you bring two atoms close together, what happens is that the transition frequency of this second atom is shifted, and within a certain distance, this transition frequency can be shifted so far that the laser that normally would excite the atom, that is resonant with the bare transition frequency is no longer resonant, and this transition doesn't occur. And we say this is sort of this Rydberg blockade mechanism. So typically there is a Rydberg blockade radius associated with this length scale where this happens, and this Rydberg blockade radius, depending on these laser parameters and the states that you use, is on the order of a few micrometers. And since this is exactly sort of the length scale where you can trap these atoms with these optical tweezers, this is sort of an ideal mechanism to make these atoms interact. And now with these ingredients, you can start building many-body Hamiltonians now by simply sort of summing up these terms according to the arrangement of atoms. So you have this single particle term and this density term that gives an energy penalty for two atoms if both of them are in this one state, which is the Rydberg state, and they depend on the distance of these atoms. Now you can sort of consider, realize different Hamiltonians here by simply arranging these atoms in different configurations. And the simplest configuration, sort of in 2 dimensions, for example, is the one where you place the atoms on a square lattice and adjust the blockade radius or the distance between the atoms in such a way that the blockade radius exactly encompasses sort of an atom and its nearest neighbor. And then the interactions between sort of an atom and the diagonal neighbor is already significantly smaller. And in this case, you can easily understand sort of the ground state phase diagram of this Hamiltonian, or at least the limiting cases are extremely easy to understand. The simplest case is, you have this blockade constraint here, but the simplest case in this phase diagram is just, when I realized when this detuning is here negative and is very large. So if this detuning is very large, is very negative and large compared to omega, for example, the ground state is simply the state where all individual atoms are in their internal electronic ground state. And that's sort of nice because you can actually, that's actually the state that you prepare. So if you load these tweezers, all of these atoms are in the internal ground state. And in that sense, you can prepare the ground state of this Hamiltonian at a specific point in this parameter space with a very high fidelity and a very low entropy. On the other hand, if you go sort of to large positive detunings, what you see is, well, you know, there now this term here is positive, and you can lower the energy of this Hamiltonian by simply putting as many atoms in the Rydberg state as you can, while you know, simultaneously satisfying this blockade constraint that no two neighboring atoms can be in the Rydberg state. And it's very easy to see that on the square lattice, you have basically two configurations that maximize this Rydberg number here, which are these two checkerboard type configurations where on one sublattice of the square lattice, all atoms are in the Rydberg state, and then the other one, all are in the ground state, or vice versa. And sort of course, this breaks spatial Z2 symmetry. So what you expect is that, you know, when you tune this laser from negative to positive, at some point, there should be a quantum phase transition that, you know, reflects the fact that you have a symmetry breaking here. And what you expect from sort of general arguments is that this quantum phase transition is in the Ising universality class. And just as a reminder, you know, what does it mean that you have a quantum phase transition here? And what are sort of the essential aspects of this quantum phase transition? Well, you know, generically, if you have a second order quantum phase transition, what happens is, you know, if you start out, if you have a system here in the disordered phase and you have a control parameter that, you know, you can tune to go from the disordered to an ordered phase, what happens is, for example, that the energy gap closes at the critical point, and it closes in a particular way as a power law with a certain, you know, exponent here. At the same time, when you approach this critical point, your correlation length diverges algebraically again with an exponent u, which is the correlation length critical exponent. And the point is that, you know, this behavior close to the critical point, you know, the way the gap closes and the way the correlation length diverges is only determined by a universality class of the phase transition, and not really by the microscopic properties of your Hamiltonian, of your system. And for this Ising universality class that sort of we expect to, you know, be realized here in this system, these two, you know, exponents that are relevant here, the dynamically critical exponent z is known to be 1, and the correlation length critical exponent is known to be this 0.2699, some numerical value which can be, you know, calculated from Monte Carlo or, you know, conformal field theory bootstrap approaches. So this is the Ising universality class in 2+1 dimensions, and that's what you expect. You can do numerics and indeed confirm by some sort of finite size scaling analysis using, I mean, this is a study that we've done with Ryan and Subia Sachdev at Harvard, using DMRG on sort of finite cylinders, and then do finite size scaling. You can indeed, you know, locate the critical point and confirm that all the critical exponents that you sort of can check are consistent with what you expect from an 2+1 dimensional Ising universality class. Now the question is, of course, that's nice that we can characterize this, but can we sort of see this? Can we see this quantum critical phenomenon in an experiment? And how can you probe this? And one way to probe it is that you can use dynamics, quantum many-body dynamics across this phase transition. And the way to do it is the following. So, you know, what you can do in this experiment is you can start out with the ground state of the Hamiltonian on this disordered side, where, as I said, you know, you can prepare the ground state with a high fidelity, and then you can sort of slowly change dynamically this control parameter and try to sweep it from this disordered side to the ordered side. And you want to do it, you know, as slow as you can, such that, you know, you stay adiabatic with respect to these excitations here. But you have to do it at some sort of finite speed. And what happens is, of course, if you do it slowly, the system initially will follow the instantaneous ground state, and sort of the correlation length will grow accordingly if you're staying adiabatic. But since you're going at a finite speed and the energy gap closes, eventually you will reach a point where you can no longer be adiabatic with respect to this energy gap, and the system, you will create excitations, and correspondingly these correlation lengths can no longer follow this divergent behavior, and you will end up with some sort of finite correlation length. And from this simple sort of picture, you can deduce that there will be a scaling relation between the correlation length in the ordered phase and the sweep speed, or the time you use to sweep across this phase transition, which will only be determined by the critical exponents of the universality class of the phase transition. So that's nice, because in this dynamic way, we can probe properties of the phase transition here, and you can set out to do so now in an experiment, and that's what they've done at Harvard. This is exactly what I sort of had in the comic before. In this, they turn on the Rabi frequency, and then they sweep the detuning from some negative value to some positive value with a sort of linear schedule at a certain finite speed, and then you can sort of measure at various points in the sweep. You can sort of calculate the density correlation function and extract the correlation length, and you can plot it, and you can do these things now for various sweep rates. Take a different total evolution time and do it faster or slower. And what you find is that you get indeed a behavior that you expect, at least qualitatively, that the correlation length grows, but sort of it grows much stronger to larger values if you go slower across this critical point. And what this Kibble-Zurek scaling hypothesis now predicts is that all these data points should collapse onto a single scaling function if one rescales the control parameter with and sort of the x-axis and the y-axis with the sweep rate, or more precisely as a function of the sweep rate that involves these critical exponents of the quantum critical point. So if you rescale this the y-axis and the x-axis in this way, then you indeed see a very nice collapse of all these data points. And sort of in principle, you want to use this to confirm that your universality class is really the 2+1 dimensional Ising model. And so what you have to note here is that there are essentially three parameters that are sort of unknown a priori. One is this critical point. The other one is Z, and the last one is nu. And of course, from just a single scaling collapse, you cannot determine all three of them. So what we did is we independently determined the value of the critical point by measuring the susceptibility as a function of the tuning and seeing where it peaks. We assumed that Z is 1, which is a natural assumption for Lorentz invariant field theory at the critical point. So at least it's the least controversial assumption that you can make. And then we looked at which value of this nu, which would come to the correlation length critical exponent, leads to the best data collapse here. And this is shown here as an inset, where this quantity D basically is a measure of the difference between these different data points. And you can now look for which value of nu sort of minimizes this difference and leads to the best collapse. And indeed, what you see is that the value of nu that gives you the best data collapse is at around 0.62, which is in very good agreement with what you actually expect for the 2+1 dimensional Ising transition. And in particular, it's very clear that it's not 1, which would be the value of the critical exponent for a 1+1 dimensional Ising model, which was actually also observed using Kibble-Zurek dynamics a few years ago in one-dimensional chains. And it's also reasonably far from 0.5, which would be the correlation length critical exponent that you would expect if this system would be described by mean field theory. So that's really nice. And as far as I know, I think it's the first observation of a quantum critical phenomena related to the 2 + 1 dimensional Ising model in quantum many-body system. And it really highlights sort of the use of this Rydberg this atom array platform to really, study quantum critical phenomena in a many-body system. Of course, what I've shown you here now is sort of the simplest case in this phase diagram of the 2D square lattice, which is sort of depicted here, which we obtained from DMRG. So sort of on the x-axis, this is again the detuning. On the y-axis, what is plotted here is essentially the blockade radius, or the inverse distance between these atoms. If you bring these atoms closer and closer together, then the system hosts a whole series of various ordered phases. And in principle, you can explore them all just experimentally by bringing the atoms closer together. And I mean, I can go through all these phases. Sort of we so far, looked at the transition from the disordered to the checkerboard phase, which is this one here. So yellow here corresponds to an atom being in the Rydberg state, and black corresponds to an atom being in the ground state. And so if you go up this line, you will see a sequence of sort of classically ordered states, which simply, you can simply understand by considering sort of larger and larger blockade radius and consider the, according closest packing solution of excitations on the square lattice. And, there are different phases with different sort of that break different translational symmetries. But what's curious is that there are also other phases that order differently than any of the classical phases, and are only present sort of at the finite value of a transverse field, and sort of in that sense are stabilized by the presence of quantum coherence between ground and Rydberg state. And for example, this striated phase is one of them. And you can easily understand what's going on here if you sort of think about it coming from this checkerboard phase. If you are in the checkerboard phase breaks the sublattice symmetry between the two sublattices on the square lattice. And if you sort of increase the blockade radius, you will undergo a second order phase transition to this striated phase, in which one of the sublattice, which is the active one where you have Rydberg excitations, now further, in this sublattice, which is also a square lattice, you further break the sublattice symmetry within this sublattice, and you go into this striated phase. And one way to understand it is the following: if you think about this star phase, the star phase is actually in the very classical limit. If you don't have a Rabi frequency, it's all in the ground state manifold of the star phase is actually almost highly degenerate, or approximately degenerate, in the following sense. If you think about the blockade radius being square root of 2 times the lattice distance, so such that the Rydberg atom blocks its neighbor and its diagonal neighbor, then sort of this column here, you could in principle also move up on one side, right, without sort of violating the blockade constraint. But what selects sort of what breaks the symmetry, what breaks the degeneracy between these ground states are Rydberg interactions beyond the blockade radius. So there is a Rydberg tail, which, because these Rydberg interactions have this 1/r⁶ dependence, which of course favors this configuration over the other one, where this column is sort of shifted up by one side, because the interaction here is at the distance 2, while the interaction here is at the distance 5. So this configuration is the one that is classically favored. But if you now have a finite transverse field, you can actually lower your energy by sort of paying the small price of moving this column here up one side, sort of getting to this configuration. So if you do that, you have to pay the price of these long-range Rydberg tails. But what you gain is that you free up sort of this side here in the middle between these Rydberg excitations, that now, here there is no side that has no direct neighboring Rydberg excitation, but here you have one that now can sort of partially align with the transverse field and lower the energy by doing so. So in that sense, you can understand how this phases emerge that have no classical counterpart in the sense that if you turn off the transverse field, they disappear. Since all of these phases, have different break different spatial symmetries, you can experimentally identify them simply by looking at the structure factor, and all of these phases have now peaks at different momenta, and by sort of looking at these peaks appear for the different phases, you can sort of map out experimentally the phase diagram. And if you do, all of these states are sort of prepared in these quasi-adiabatic sweeps, and then measured several times to look at the structure factor. And if you do that, you get actually fairly good agreement between sort of the experimental determined phase diagram and what you would expect from DMRG, at least on sort of finite system sizes. What you also can do experimentally, which I find really nice, is that you can now measure things like this quantum coherence between the different configurations that actually stabilizes these striated phases that are otherwise not there in the classical limit. And the way to do it is, well, you can see that in the striated phase, essentially you have two inequivalent sites on one of the sublattices of the square lattice, and on one side your atoms are mostly in the Rydberg state, and then the other one your atoms are mostly in the ground state, but they have some sort of component also in along the x-axis. So in this mean field picture, at least, that's the ground state in the striated phase, and you can now probe the coherence between the ground and the Rydberg state on the two different sublattices by doing essentially some sort of many-body spectroscopy. Or if you want, you can, each of these sites has sees a different mean field shift. Sort of these gray sites see a pretty large mean field shift from the presence of these nearby Rydberg excitations, while the black sites see a smaller Rydberg shift, because a smaller mean field shift, because the nearby sites only have a very small probability to be in the Rydberg state. So you can, energy selectively drive the different sublattices, and you can see at which energies they respond, and you can, probe their phase sensitivity to the sensitivity to the phase of a drive at a particular, frequency, and from looking at this phase dependence. Looking at this phase dependence and sort of the response at the different frequencies, you can actually infer the Bloch vector on the two different sublattices and see that indeed in the striated phase, the Bloch vector has a non-zero component along the x-axis. Okay, that's all I wanted to say about the square lattice. Of course, you can now have even more interesting physics if you change the lattice geometry, and you can go to sort of more complicated lattices. Experimentally, the beauty is that you don't have to do that much to do so, and you can probe all of these things. So what we did theoretically analyze is, for example, what happens if you place atoms on the edges, on the vertices of a Kagome lattice. And what's nice is that sort of at large detunings here, there is an approximate mapping to dimer models, to different types of dimer models, depending on the value of the blockade radius. And in particular, these dimer models host the same type of ordered ground state as the Kagome lattice, and they also host topologically ordered sort of spin liquid states. And we asked the question whether one can see signatures of this topologically ordered state also in the Rydberg model. And sort of from the numerics that we did together with Ryan here, we have at least some numerical indications that there is a possibility for such liquid states in these models. There are other works by Ruben Veresen and Ashwin Vishwanath that looked at different types of lattices where you place now atoms at the links of a Kagome lattice. And what's nice here is that in the limit where the tuning is very large, the Hilbert space actually exactly maps onto a dimer model on the Kagome lattice. And that's a very strong indicator that in the ground state of this model here, there might be a Z2 spin liquid. And the numerics that they have here indicate at least that indeed this spin liquid phase is realized in this Rydberg Hamiltonian here on this Ruby lattice. But I don't want to talk too much about it because, first of all, there is another talk in these VAMOS seminars 2 weeks from now by Giulia Semenghini, who will exactly talk about the physics related to this type of lattices. And I don't want to steal the show here, but it's very exciting, and I encourage everybody to attend that seminar. Okay, with this, I'm at the end of the first part of my talk regarding many-body physics in this Rydberg arrays, and if there are questions for the first part, I would take them now.
Sounds good. Yeah, there's quite a few questions. Won't get through them all, but we'll do a couple. Bill Phillips asks a question. Could you say a little bit more about the assumption that the dynamical critical exponent z is equal to 1? In particular, what makes this a good assumption? What could make it a bad assumption? And are there prospects for directly measuring it in the experiment?
Yeah. Sorry. Yeah, I mean, I think I would say that the assumption that z is equal to 1 is sort of a natural one for the dynamically critical exponent. I mean, whenever you have a critical point which is described by a conformal field theory, I would say the assumption that z is equal to 1 sort of is underlying that. So whenever you have sort of emergent Lorentz invariance, you will have a dynamically critical exponent of z equals 1, and in most quantum critical points that we came as sort of that's actually realized. There are a couple of models, especially in this Rydberg atom array business in 1D, where this might not be the case. These are related to these chiral clock models, but if you believe that there is a conformal field theory at the critical point, then z equals 1 is a natural assumption. And regarding the other question, whether you could potentially measure that, I think, yeah, there would be a couple of ways in which you can measure it. I mean, if you could go and park at the critical point, you could try to do sort of modulation spectroscopy to map out the excitation spectrum. And in that way infer the critical point. You could potentially probably also make other types of measurement of this Kibble Zurek type and sort of determine more than one critical exponent from these measurements. But I think the most straightforward measurement would just be doing sort of excitation spectroscopy at the critical point, or for example, measure the gap as a function of the size of the system at the critical point again. So if you take different sort of patches of 2D arrays of atoms at different sizes, and you are able to sort of measure the minimum gap, then by again sort of modulation spectroscopy, or by sort of just going across the critical point and trying to be slow compared to the finite size gap, then by sort of figuring out how slow you'd have to be, you can sort of infer how big the finite size gap is, and from that you could in principle also determine the exponent z. Yeah.
Very good. Ashwarya Kumar has a question. Is there different and also interesting Ising physics to be expected in 3 dimensions? And are there prospects for also probing that with tweezers?
I mean, the 3D Ising universality class is different from the, like the 3+1 dimensional Ising universality class is different from the 2+1 dimensional. How different it is in practice, I'm not so sure. Yeah, regarding the prospects of studying is with tweezers, I think it's actually in principle possible. I mean, there are groups in France, Antoine Brevet, who already sort of assembled atoms in 3-dimensional arrays. So I think it's only a matter of time before people will actually start studying that. I mean, there is no fundamental reason why this should not work in the near future, actually.
Great. And Francisco Machado has a question. He wonders, for the phase diagram on the square lattice, are any of the ordered phases strongly entangled? And are all of the phase transitions expected to be second order and continuous? Or can one imagine that some of them should actually be first order phase transitions?
Yeah, I mean, all these phases are not strongly entangled. These are just symmetry breaking phases. And they are basically product states here. On this side, all of these states are product states, and you can describe it by mean field theory. Sort of at least all of them that we looked into sort of carefully are essentially captured within sort of, you know, a mean field model. Regarding the nature of the phase transition, I mean, this we studied in detail the transition from this disorder to the checkerboard, which is indeed continuous. We also know that the transition from the checkerboard to the striated phase is a second order transition. But then these transitions, you know, up here between these different classically ordered states, they are actually first order. So in that sense, yes, there are the transitions of different order. But for example, I don't know exactly what type of transition between, you know, the disordered and these staggered or banded phase. What's the universality class of these transitions? I'm actually not sure about. And we didn't look into that.
Okay, great. There's a couple of other questions, but we'll let you continue for now and come back to them.
Okay, great. Yeah, with that, I'll move on to the second part of my talk, and we'll sort of basically frame whatever I said now a little bit different and bring it into the context of quantum information. But you will see sort of from a physics point of view, it's actually pretty much the same thing. But you know, if one talks about and thinks about it differently, one can ask different questions and cover sort of interesting physics there. And what I wanted to talk about in the second part is about quantum optimization, and in particular quantum optimization of a particular problem, which is very much related to Rydberg physics, which is this independent set problem. So independent set problem, for those of you who don't know it, it's a sort of paradigmatic optimization problem in computer science, where I give you a graph with a certain set of vertices and edges, with a challenge to find the largest number of vertices on this graph that are not connected. And sort of that's what an independent set. An independent set is just a subset of vertices that are not connected. The largest one is sort of the challenge to find. And on this sort of toy graph here, I indicated two different independent sets with red vertices, and the one here on the right is indeed the largest one. For this simple small graph, it's very easy to double check that this is indeed the largest one that there is. But of course, if I make the graph larger and larger, the problem will become actually pretty soon very hard. And the reason is that this maximum independent set problem is one of these important CARP's NP complete decision problems. And so even finding an approximate solution is NP hard. And so in that sense, it would be an interesting problem to solve, or at least try quantum algorithms that are sort of aimed at solving this problem, sort of at least semi-efficiently. Okay, but to do so, let me first sort of formulate this maximum independent set problem in a form that makes it amendable for, or that is useful for thinking about quantum algorithms, and that is sort of, first you want to formulate it in a Hamiltonian way. So you write down a classical Hamiltonian that encodes the solution of this optimization problem in its ground state. And the way to do so is you associate with each vertex a binary variable, a classical binary variable, which is either 0 or 1. And then you write down a Hamiltonian which has this form, which basically counts the number of vertices that are 1 here, that are red. And it gives an energy penalty to configurations if two vertices are connected and both red. And I mean, obviously this Hamiltonian here encodes the maximum independent set as a ground state in the following sense. If this delta is negative, then the ground state is a trivial one where all vertices are white. But if this delta is between 0 and V, then you would like to put as many vertices, you would like to color them red, up to the constraint that no two neighboring vertices on the graph have to can be red. And so this is a Hamiltonian formulation of the maximum independent set problem, and it's obviously very related to the Rydberg physics, because this is essentially the classical part of this Rydberg Hamiltonian that I wrote down before, with the only exception that here the interactions are blockade interactions between vertices that are neighboring on an arbitrary graph, whereas in the Rydberg problem you had interactions that had a geometric structure that owing to sort of the Rydberg interaction profile. Okay, so you can now go ahead and follow two routes. You can either say, okay, let me try to engineer Rydberg atoms in such a way that I can encode arbitrary graphs in their ground state, or I can take a different approach and say, well, let me look only at graphs where that I can realize with Rydbergs naturally. And such graphs, for example, are called unit disk graphs. Unit disk graphs are just graphs which I obtain if I place vertices on the 2D plane, and I connect them if and only if they are within a certain unit distance. And I can now ask, I can now formulate this maximum independent set problem on these unit disk graphs, and ask you to sort of find the largest one. And the question is, okay, if I restrict my problem now to unit disk graphs, does it become easy? Sometimes if I restrict the problem to a certain set of graphs, then I introduce so much structure that it's actually easy to find the optimal solution. And but importantly, for these unit disk graphs for maximum independent set, it turns out you can prove that it's still NP compared, at least in the worst case. Finding the exact ground state is hard. However, of course, it's kind of subtle, because it turns out that finding approximate solutions on unit disk graphs is not that hard, in a sense that there exist polynomial time approximation schemes that have a runtime which is polynomial in the size of these unit disk graphs and the number of vertices. But sort of the power of this polynomial is dependent on the approximation ratio that you want to achieve. So if you want to find a solution whose size has a certain fraction of the actual maximum independent set, if you make this fraction very close to 1, this power here in the polynomial becomes very large, and the runtime becomes very large. So that's how these two statements sort of are reconciled. So finding the exact ground state is actually still NP complete, and you can sort of test that this is not only true for the worst cases, but even if you sort of draw random unit disk graphs and sort of look at the average case hardness for sort of generic branch and bound classical algorithms that try to find the exact solution of these graphs, you can see that the runtime is sort of super polynomial, at least in a certain parameter regime of this phase diagram, where you have the vertex density here as a parameter. Of course, if your vertex density is very low, is sort of below the percolation threshold, then your graph decomposes and classical algorithm has a very easy time to find a solution. If your vertex density is very high, then you essentially try to solve the closest backing problem in the continuum, which is also very easy. But sort of for the proper density, it's not easy on average to find the optimal solution. And if you want to do this with Rydberg atoms, you can even sort of make it more simple. Yeah, you can restrict your class of graphs to sort of something that I call more experimental friendly graphs, where you place your atoms, for example, only on the vertices of a square lattice or with a certain probability, and choose a blockade radius that is larger than square root of 2. If it's smaller than square root of 2, then the graph is bipartite, and then it's simple. But if it's larger than square root of 2, then it's again an NP complete problem. You can even make it even simpler and place the atoms on the vertices of a triangular lattice, then all the instances become sort of planar, but it's still NP complete, even if you restrict your class of graphs to this type of unit disk graphs. Or you can use other unit disk graphs where you say, okay, maybe I don't allow vertices to be at a certain distance with each other. For example, I don't want to have vertices very close by because I cannot trap atoms in tweezers very close by. And you can ask, does this sort of change anything? But for all of these instances, you can very easily prove that this thing, maximum independent set, is still NP complete. And if you run sort of these branch and bound algorithms, you can see that even sort of an average case, they always show a super polynomial scaling for classical runtimes. But the reason I'm bringing this up is because there is a subtle difference in unit disk graphs and Rydberg Hamiltonians, which is that the Rydberg Hamiltonian has a long 1 over r⁶ tail, and the unit disk graph doesn't. And if you take a random unit disk graph, you can have instances where you have two vertices that are just outside of the unit distance. So according to the maximum independent set problem, they should be non-interacting, but the Rydberg Hamiltonian actually has them almost interacting as strongly as the blockade interaction. And this can lead to sort of structural changes in the ground states. And if you sort of devise quantum algorithms that try to find the ground state of this Rydberg Hamiltonian, or that try to find a maximum independent set based on trying to find the ground state of the Rydberg Hamiltonian, this might be a problem. And indeed, if you sort of do numerical simulations, you see that for random unit disk graphs, the approximation ratio achieved by the ground state of the Rydberg Hamiltonian with respect to the maximum independent set is actually not that great. But if you sort of restrict your class of problems to these type of things that by construction don't have vertices just at distances just outside of the blockade radius, then you can see that you can essentially avoid this problem with extremely high probability. Okay, so with this, let me just briefly jump into sort of how quantum algorithms for this thing would work now. And this is very similar to what we already did on the square lattice. So essentially, you write down your Hamiltonian, which now has some sort of time-dependent control parameters, like the ones we used before, the detuning, the Rabi frequency, or maybe the laser phase. You place the atoms according to where your unit disk graphs would have vertices. You choose your Rydberg blockade radius, according to the unit disk radius. And then, you drive with this Hamiltonian, the system initially prepared with all atoms in the ground state, with some sort of, functional form of your control parameters. You prepare some sort of variational state, and you measure the system. And you hopefully drive the system in such a way that it ends up close to the ground state. And if it doesn't, you can sort of optimize your variational parameters in order to drive it close to the ground state. And you do this in a closed feedback loop. And sort of the heuristic idea is that this type of thing might allow you to find good solutions for this maximum independent set problem, or any sort of problem that you address with quantum optimization. And so at Harvard, we sort of have preliminary results for doing these things. We looked at this 179 vertex unit disk graph, which is just obtained from the square lattice by removing a certain fraction, 20% of the vertices. This unit disk graph has a maximum independent set of size 57. And if you just run a very sort of simple adiabatic or quasi-adiabatic linear schedule, many times, you can sort of collect a histogram of the configurations that you find in the final state. And what you see is indeed you get the maximum independent set with a certain finite probability, which is sort of limited by on one hand finite evolution time, but sort of it's non-zero even on these like really substantially large graphs. You can sort of see that the average number the average size of the independent set is a little bit smaller than the maximum one. You miss on average 5 sites. But maybe the average number is not really that important. What you really care about is because if in some instances you get sort of a very poor result, you don't really care. You just run the algorithm again. So what you care about is sort of the best solution of sort of the best subset of shots that you have. And one way of quantifying this is to look at this conditional value at risk, which just tells you what's the mean of the top half of the shots. And in this case, it was 54. It's already quite close. What you can do then is to do some sort of variational optimization, right? The simplest thing that you can do is you can, make your schedules in such a way that there is some part where you go slower than in the rest, and you can vary where you go slow. Sort of anticipating that there might be somewhere a minimum gap, and there you would like to be slow. And indeed, if you do that, you can see that if you look at this conditional value at risk as a function of where you go slow, you can actually improve the figure of merit here, monotonically up to this maximum, and then it goes down again. And in that sense, variational optimization actually helps improving, helps finding a better solution. And more than that, you can even see that before there was with just a linear schedule, you found the maximum independent set, 14 times out of 5,000 ones. And if you sort of optimize your function here a little bit with just one variational parameter, you can, get a factor of 3 in this MIS probability here. Of course, there are also other optimization algorithms that people have proposed rather than this sort of very naive adiabatic or quasi-adiabatic schedule that we have used so far, which are these quantum approximate optimization algorithms, which basically are, when you translate it to these Rydberg Hamiltonians, they consist in an application of a sequence of pulses with different pulse durations and different either the tuning or laser phase. And these parameters are now your variational parameters. So in the shortest depth quantum optimization, quantum approximate optimization algorithm would just be a single, resonant Rydberg pulse, resonant laser pulse that couples the ground state to the Rydberg state. And what you see is that if you take now your, pulse duration as a variational parameter, you see that indeed already at rather short times, sorry, this should here be like a pi/2 time almost, you get sort of the maximum Rydberg density, which is at, this is the same graph that I had before. So the maximum independent set size here is 57. With a single, depth p equals 1 QAOA, you only reach a conditional value at risk of 35. If you add another layer, you can significantly improve on that. And so the best variational state that we get with a p equals 2 QAOA, which is very short evolution time. So in total, this is just something like a few 100 microseconds. You get a conditional value at risk which is 41. So you can definitely see an improvement from p equals 1 to p equals 2. It's still not yet at the level where what we get when we do sort of an adiabatic sweep, but that's what you get for a very short depth QAOA. The question is, of course, can you improve further and further if you make this circuit deeper and deeper? And one challenge that you face there is then that the classical optimization becomes very hard. Because you have more and more variational optimization parameters. And what we did in this study below here is that for a slightly different problem, we actually looked at the patterns of the optimal solutions here for sort of short and medium depth QAOA. And what we found is that for many instances of graphs, they typically fall onto sort of a very specific trajectories. And based on that observation, you can now come up with heuristic algorithms to try to, pre-compute good seeds for this classical optimizer. And we did try these algorithms and found that they're pretty good at finding good variational optima, even for sort of reasonably deep QAOA algorithms. It's not really. I mean, we can only do this sort of numerically for rather small system sizes, and we cannot really make a statement about how this QAOA sort of then scales with system size, what's the performance. But for that, we would eventually like to do this, of course, on a coherent quantum machine. What one can also do numerically, at least, is to sort of look at, what's the time to solution that, the optimal QAOA parameter set takes. So this time to solution is a measure that takes into account the coherent evolution time and the fact that you can have to that you can repeat the measurement, several times and get different shots due to quantum fluctuations. And if you repeat them, you might actually find the solution eventually. So this is a quantity that measures this time to solution, and you can try to correlate it to something like the minimum gap along an adiabatic trajectory. You can ask, okay, is this QAOA algorithm doing something better than what you would expect from adiabatic algorithm, where the minimum gap is a proxy for the performance? And indeed, what you find is that if the minimum gap is actually pretty substantial, then the quantum approximate optimization, time to solution is strongly correlated with the minimum gap, and they have a similar performance. But there are, for graph instances where the minimum gap is very, very small, you can actually find, variational optimas that substantially outperform something that would be bounded by the minimum gap. And I think the physical reason that we believe is at work here is that this quantum approximate optimization algorithm can excite you to an excited state before you cross the minimum gap, and then you can undergo a diabatic transition where you go back to the ground state during the propagation with this quantum approximate optimization algorithm. But of course, there are many questions that are open. Of course, the most pressing ones are, what are the performance and scalings of these quantum approximate optimization algorithms with problem sizes? How does this performance depend on different graph instances? Is it different for unit disk graphs, and in which way is it different for unit disk graphs than other graphs? And many of these things, cannot really be addressed, with classical computers, simply because you need to simulate dynamics of many body systems. But the idea is now to use quantum machines with Rydberg atom arrays and try to test these things and answer these things, at least on an empirical level. Okay, this is my last break point, and afterwards I have 5 to 10 more slides, but maybe I can take a few questions here.
Okay, maybe let me suggest, since we're maybe running a little bit behind schedule, let's continue, and we'll table questions for the end.
Okay, sounds good. Okay, then in the last part, I want to just talk about one other application which is very closely related to this optimization with maximum independent set, which is sampling. So another task you can try to use these Rydberg atoms at is to do sampling from a classical probability distribution. And the challenge here is, you're given a probability distribution like, a Gibbs state. Maybe you're not really given the probability distribution, you're just given a classical Hamiltonian, and your task is to produce samples from this classical Hamiltonian according to the, thermal state. And in the example that we had before, which is this independent set, you would just be asked to, produce, some of these samples with the according probabilities that the thermal state would give you at the given temperature, which is the error parameter. And, the idea is to use quantum system here. So the high level idea is to prepare now a quantum state, which is just a superposition of all, configurations with the amplitudes, which are just the square roots of the probabilities. So obviously, if you can prepare such a state, you can sample from this distribution by simply measuring in the computational basis. The real challenge is, of course, how can I prepare such a state, and can I do this efficiently? And of course, this is a question that people in quantum information science have asked before, and come up with general quantum algorithms to do so. What we would like to do here is to come up with an easy way of doing it in an experiment that can be done in the near term. But before telling you how to do so, let me just briefly remind you how you would do it with a classical machine. So if you want to produce samples from a distribution with a classical computer, what you do is you can use, for example, a Markov chain Monte Carlo algorithm, where you basically say something like, okay, let me start with a random configuration, and let me try to flip a spin now. Let me make an update rule where I flip spins according to some probability, and generate new samples by single spin flip updates. And if I choose this, update rule correctly, what I'm guaranteed is that after a certain number of steps, I produce a new sample here from my starting sample that is statistically independent from it and is distributed according to the probability distribution that I want. And in general, this sort of Markov chain is described by a stochastic matrix, which tells you, how to go from one step to the next. And if you can write down such a Markov chain. The nice thing is, when you have one, you can also write down a quantum Hamiltonian in such a way that the quantum Hamiltonian has this Gibbs state as its unique ground state. So essentially, what you do is you conjugate your Markov chain with this operator here, which is just a classical Hamiltonian, and it's very easy to see that this Hamiltonian, because the Markov chain, the stochastic matrix, the spectrum of the stochastic matrix is bounded in absolute value by 0 and 1. So the spectrum of H is also bounded by 0 and 1, and it's easy to check that the Gibbs state is an eigenstate of this Hamiltonian with 0 eigenvalue. So it's the ground state of this Hamiltonian, and in that sense, the challenge is reduced to preparing the ground state of such a Hamiltonian. Okay, and let me just tell you how this Hamiltonian looks like. For example, if I start with a Markov chain that would correspond to single spin flip updates on for independent set problem, if I take single spin flips here and I use my Gibbs distribution for the independent set problem here, and I calculate this quantum Hamiltonian, this is what I get. It looks like an ugly Hamiltonian that contains sort of some non-local projectors, and looks rather hard to implement. But the nice thing is, if you sort of stare at this long enough, you can see that, for example, if you look at the simplest example, which is sort of a 1D chain, then this Hamiltonian actually boils down to exactly the Hamiltonian of the Rydberg atom array. So it contains a coherent drive, a detuning, nearest neighbor blockade, and next to nearest neighbor interaction. And these parameters here are now dependent on sort of the temperature, which is a parameter of the probability distribution from which I want to sample. And the ground state of this Hamiltonian for different values of these parameters correspond to different Gibbs states at different values of beta. Now you can look at sort of this Hamiltonian, look at the phase diagram, as a function of V and omega. And what you see is, of course, there's a one parameter family where the ground state corresponds, are the Gibbs states at different temperatures. Sort of here is the infinite temperature Gibbs state, and here's the 0 temperature Gibbs state. And if you would sort of try to prepare these Gibbs states, one thing that you can do is you can start with the infinite temperature Gibbs state and then try to adiabatically follow the ground state here to your final temperature, for example, to the 0 temperature one. And what you see is that you will take time to reach the state, which is scaling with the 4th power of the system size, which is the same time that sort of the classical single spin flip Markov chain takes, because this is sort of an activated diffusion problem. Now, if in a quantum algorithm, what you can do is you can either you're not bound to sort of stay on this line. You can also deviate from it and perform an adiabatic passage along a different trajectory. And what you know is because that you can sort of cross, for example, the phase boundary here, and from the properties of this phase transition, you expect that you can do this and reach this point now at a time which scales only linearly with system size. So if you deviate from this thermal trajectory and sort of come to your final point via a different path, then you can actually outperform sort of the competing sort of classical Markov chain Monte Carlo algorithm. Of course, this 1D example is sort of a pathological one in some sense, because only sort of 0 temperature is really interesting. You can also find examples where you have a finite temperature phase transition, and you can have a similar sort of polynomial speed up when you compare the quantum sort of path versus the Markov chain Monte Carlo algorithm. And you can sort of also come up with implementations with Rydberg atoms for sort of more complicated graphs that are not 1D chains. So if you consider, for example, unit disk graphs and you want to sample from unit disk graphs, what you see is that the corresponding parent Hamiltonian is now exactly the Rydberg Hamiltonian with blockade approximation, but it also contains an additional multi-qubit term. And this multi-qubit term, even though it's multi-qubit term, typically it would be quite annoying if you would consider sort of problems that are not necessarily this maximum independent subproblem. But for this maximum independent subproblem, this multi-qubit term that appears here is actually quite simple. It's just a conditional energy shift. So your ground state energy should get a shift if all the neighbors are also in the ground state. And you can very easily sort of come up with ways of realizing such a term with Rydberg atoms by, for example, simply dressing the ground state with another Rydberg state in such, and that would that would give you an AC Stark shift, but it would only give you an AC Stark shift if no neighboring atom is in the Rydberg state. Otherwise, sort of this changes the level scheme over here, and this gives you a conditional AC Stark shift, which is exactly what you need to realize this parent Hamiltonian that you want here. Okay, with this, I'm basically done. I just want to quickly summarize. So what I've shown you in the first part of my talk is, I hope I've convinced you that these Rydberg atom arrays are a very versatile platform to study many-body physics and quantum many-body physics, close to equilibrium. There's of course also a whole different story about many-body physics out of equilibrium that can be addressed with these Rydberg atom arrays, but I didn't have time to talk about today. In the second part, I talked about quantum optimization. I hope to have convinced you that this platform is ideally suited to test some of these quantum optimization and quantum sampling algorithms and see how they actually perform on real quantum hardware. And with that, I realized I'm out of time, but I definitely should take the time to acknowledge the people that are involved in this project. So this is sort of the experimental team that really does the hard work in the lab at Harvard. These are my theory collaborators. In particular, I would like to highlight Ryan here, which did a lot of the numerical simulations for this 2D square lattice and Kagome lattice. He's a student of Subia Sachdev. And I would also like to highlight Dominic Wild, who is the brain behind this sampling project that I talked in the last part. And of course, these are sort of the PIs that are running the show at Harvard and MIT. Okay, thanks for your attention.
All right, we've accumulated quite a non-trivial list of questions, Hannes. We'll try to get through a couple of them, but for those of you, if I don't get to ask your question, please join Hannes in the after seminar discussion. Let me start with a question from Emily Davis. She asks, for the quantum optimization approaches you described in the second part of your talk, can you comment on whether there are differences in expectations for improvements for either the worst case or the average case of MIS?
I honestly don't know the answer to the question. It's a very good question, but I think, for these unit disk graphs, I think what my expectation is, at least, and that's very much guided by the fact that how classical algorithms perform on unit disk graphs, is that in the worst case, it will be very hard to find a solution, simply because it's an NP complete optimization problem, and you don't expect a quantum algorithm to solve an NP complete optimization problem in the worst case, sort of in any polynomial time. So I guess that will be very hard. On the other hand, for approximate optimization, in the average case, it could definitely be. Yeah, I'm not sure if I really can make a strong statement about average case versus worst case, but it's easier to think about the problem in sort of finding the exact ground state versus finding an approximate ground state. And in that case, there's definitely a difference, which is that there is a polynomial time algorithm for approximate solution, And one can probably sort of, I would expect that one can come up with arguments that allow you to, at least for some classes of graphs, tell you whether there is an average, how hard it is to find an average solution based on similar arguments that allow you to find sort of good approximate solutions, because essentially they make use of the geometric structure of the unit disk graphs. And I would expect that if you have, for example, certain constant densities, then that the average case hardness might not be that hard. But it's very hard to make a statement about a quantum advantage of these algorithms for average or worst case, simply because these are heuristic algorithms and not very much is known about it. Yeah.
Okay, one very last question. Maybe we'll go back to part one. John Simon wonders, is it possible to nucleate multiple crystals around defects, for example, induced by local Stark shifts applied to individual lattice sites, and to use this nucleation to explore effects of frustration?
It's definitely possible to nucleate sort of different crystals with different lattice sites. What definitely happens, for example, in these experiments, is that they're nucleated at the boundary. So that the boundary, you see here, the boundary is differently ordered than the bulk. So that's already sort of an indication of the effect that you mentioned. You can do this not only by playing around with the boundary, but you can even sort of have, as you say, sort of additional sort of the tuning terms or shifts at the boundary. And this has been exploited, for example, in 1D to to do the opposite of what you want to do. You want to nucleate a specific configuration, but you can also sort of make sure that two configurations are completely degenerate. And that has been exploited in 1D to generate GHZ states of two different configurations. But sort of the physics is essentially the same. So in that sense, yeah, you can influence sort of which configurations of crystals you prefer or disfavor. Whether you can do that to introduce frustration, yeah, I mean, in some sense, that's what we do here in this optimization part, right? I mean, these graphs are an extreme case of putting like a very, very strong potential on the sites where you don't have atoms, right? And in that sense, you can induce frustration because you basically form an NP-complete optimization problem. So I guess that's sort of the other extreme of the question that you asked. Yeah.
Awesome. Okay, let me, since we're running a little bit over it, let me take this time to thank Hannes again for a really wonderful talk. And as Lisa mentioned in the chat, please join us for the post-seminar discussion with Hannes afterwards. And just let me very quickly, Hannes, share screen. If you can let me do that so I can just update everyone. So next week, we will have the quantum science seminar from Sabrina Maniscalco talking about new approaches to variational quantum algorithms. And the VAMO seminar next week will be given by Tanya Zelevinsky from Columbia University on ultra-cold molecule clocks. All right, thanks everyone.